Welcome to part 2 of my lecture series on pseudo-transients in CFD. In this part of the lecture series, I'm going to be talking to you about the characteristic length scale of a CFD domain and the characteristic speed that the effect of boundaries propagates across the CFD domain at. I'm going to be showing you how these quantities are calculated automatically by the CFD code and how they're used to calculate the pseudo time step that we use in the pseudo-transient approach to stabilize the steady-state CFD calculations. This is going to be a great talk. You're going to develop a great understanding for how steady-state CFD solutions actually develop as we iterate through steady-state solvers, and you're also going to get a good idea about what's going on behind the scenes of the CFD code and how the parameters for pseudo-transients are actually calculated. Hope you're excited for this talk. I'm really excited to bring it to you. Let's jump in and get into the material. So just starting things off with a quick recap of what we talked about in part 1, the pseudo-transient approach is a method that's used to stabilize steady-state CFD calculations. And it achieves this stabilization by increasing the diagonal dominance of the A matrix by adding an additional term, which you can see there in equation 1. And the magnitude of this additional term depends on the size of the artificial or pseudo time step delta t, which is something that the user controls. And you can see straight away from the matrix that the smaller the pseudo time step, the larger the increase in the diagonal dominance of the A matrix, and the more stable the calculation is going to be. And we'd like to calculate this pseudo time step automatically rather than getting the user to specify it manually, as this makes the approach more general. And the way to think about the way that we specify the pseudo time step approach, we can demonstrate it just with a simple example of a 2D flow over a backward facing step, which you can see here. And what we do is we're going to try and calculate a representative time for the effect of the boundary to propagate across the domain. And in this case, just for this example, if the effect of that inlet takes about 10 seconds to propagate across the domain, then we can take a fraction of this propagation time and use that for the pseudo time step delta t. And the way that we calculate this propagation time, or it's sometimes called the characteristic time for the domain t0, is we take the characteristic length of the domain, which will have units of meters, and then we take the characteristic speed for the propagation of the effect of the boundary, call that u0, divide one by the other, and that gives us the characteristic time for the effect of the boundary to propagate across the domain. And so what we need for this calculation is we need a method to calculate the characteristic length of the domain L0, and we need a method for calculating the characteristic speed u0. Once we have those, we can calculate the characteristic time and then take a fraction of this to give our pseudo time step for the pseudo-transient approach. And the focus of this talk is going to be on how to calculate L0 and U0. So starting with the length scale, L0, the trick with calculating or prescribing a characteristic length for the CFD domain is to ignore the mesh and to think of the CFD domain as an object or as a complete unit. And this is quite a useful thought exercise for you watching this talk. If you think about your own CFD case where you've created a mesh which may look something like this, think about your domain and can you visualize it as a single object that's occupied by fluid? That's what we want to do here. We want to ignore the mesh and think of the entire domain as a single object. And then what we're going to do is we're going to come up with a method of specifying a characteristic length that defines the shape of this object. So the question is, what's the appropriate length to take? And just from our example of the flow over the backward facing step that we looked at earlier, we could take the distance between the inlet and the outlet. So if we had the inlet at the left end of the domain and the outlet at the right end of the domain, this length here would probably be appropriate for L0. But alternatively, if our domain had the same shape, but we had the inlet at the bottom and the outlet at the top, maybe this length here would be more appropriate for L0. Now, this seems like a sensible approach, but remember that for our pseudo-transient approach, we need this to be general and applicable to all different types of CFD domains. And in some CFD domains, we have multiple inlets and multiple outlets. Take, for example, the example that you can see here on the slide, where we've got 2 inlets and then we've got 1 outlet in the middle. And we want some kind of characteristic length for this domain, and really we can't really take the distance from the inlet to the outlet as our characteristic length. And you could for this example, but you can imagine a more complex case maybe where you had multiple inlets and multiple outlets. It's not clear what's the appropriate characteristic length to take for such a domain. So this isn't the best we could do. Can we come up with a better approach for specifying this characteristic length? Now, an example I want you to think about is a lid-driven cavity flow, which is a very simple case that really illustrates the point that some domains don't necessarily have inlets and outlets at all. So actually, us using the idea of thinking of the distance between the inlet and the outlet is misleading. And actually, for some domains like this lid-driven cavity flow, where the top of the box is moving from left to right, and this acts to stir and move the fluid in a circular motion, there's no inlet and outlet here at all. And so actually we can't use the distance from the inlet to the outlet at all to specify a characteristic length scale. And in this case, for the lid-driven cavity flow, we would probably expect the one of the side lengths of the lid-driven cavity to be the appropriate characteristic length to take. But why is that the case? Now, the trick is to think that it's not just the effect of inlets and outlets that propagate across the domain, it's also the effect of wall boundaries. And in this case, if you think of the lid-driven cavity flow, where the lid at the top is moving at some velocity, u lid, and we start the solution where the fluid is initially stationary in the cavity or in the box. It's not moving at all. Our initial condition is 0 velocity everywhere. When we start the calculation and we start on iteration 1 and then we move to iteration 2, what's going to happen is that moving lid at the top is going to first accelerate the fluid at the top of the domain, and then that fluid is going to shear and accelerate the fluid underneath it, and so on down the domain. So what's happening here is that the effect of the wall is shearing the fluid next to it, and this effect is also going to propagate across the domain. And so from this logic, we could see that actually an appropriate characteristic length for this wall-driven flow would be perhaps the distance from this top lid to the bottom lid. That would perhaps be an appropriate distance to take for L0. But there's a further observation we can make about this case of the lid-driven cavity flow. In the last example I showed you, we started the initial calculation off with the fluid not moving. Arbitrarily in our CFD code, we set the velocity to 0 everywhere and then started the steady state solver. What if we took a different initial condition? What if we started with the fluid moving everywhere at the same velocity as the lid? So say, for example, the lid is moving at 2 meters per second and we set the entire fluid moving at 2 meters per second. What would happen then? Well, actually, if we observed the solution of the CFD code every iteration, we would see the opposite effect to what we saw before. The velocity, of course, is 0 at the walls, it has to be, and so as the solution develops, we'd actually see the effect of 0 velocity propagating away from the walls back into the domain and slowing down the fluid at the bottom, slowing down the fluid at the side, until eventually we were able to develop that swirling cavity flow in the lid-driven cavity. So this is a really important observation for us when we're trying to come up with some characteristic length for our CFD domain. The effect of stationary walls also propagates across the domain, depending on the initial condition. And actually this statement generalizes to the key observation that when we start our CFD calculation from our initial condition, actually the effect of all boundaries are going to propagate into the domain, and they're eventually going to propagate across the domain until the solution fully develops and satisfies conservation of mass, momentum, and energy. And so now if we think back to our CFD domain, we're thinking about the overall shape, we're not thinking about the mesh that's inside it. Actually, for specifying the characteristic length, we don't care what the type of boundary is. We don't care if it's an inlet, a wall, an outlet, a symmetry plane, the effect of all of those boundaries in a steady state solver are going to propagate into the domain. And so that means that the characteristic length scale L0 only needs to be representative of the shape of the domain and not the types of boundaries. Of course, there are small caveats here that, of course, in a supersonic flow, the effect of boundaries propagating across the domain is slightly different. But for your understanding so far, the key takeaway is that it's the effect of all boundaries that propagate across the domain. And so we only need to just look at this domain as a single object or as a single large shape. And because the effect of all boundaries are propagating across the domain, the first choice that we could make for our characteristic length scale might be just to take the cube root of the volume. So if we have our general 3D CFD domain, which could have an arbitrary complex shape, what we could do is we could just sum the volume of all the cells in the mesh. That would give us the total volume of the domain, and then take the cube root, which the cube root of meter cubed would give us the correct units of meters, and we could use that for our characteristic length. That's one possible choice that we could make for our characteristic length scale. However, if we think of the case of a CFD domain that's really long and really thin, say for example a really long pipe flow, then actually just thinking about it, the limiting factor that's going to control the length of time that the CFD simulation takes to converge, it's actually going to be the length of time that this boundary at the left end propagates all the way along to the furthest away boundary at the right hand end, because these walls on the top and bottom are going to propagate across the domain, but they're not going to take very much time at all to propagate from the top to the bottom of the domain. And the limiting factor for our CFD case that we're going to be using to specify the time step would actually be the distance from this wall to this wall. And so for a really long CFD domain, perhaps a better specification of the length scale would be the maximum dimension of the domain, or the maximum length of a bounding box that surrounds the entire domain. That would probably be a better approach if our domain is long and thin. But of course, in reality, CFD domains often have a complex shape, and they're not a single long thin pipe. They're not a box or a cube shaped. And this is the reason why some CFD codes like ANSYS CFX and ANSYS Fluent, if you choose to use the pseudo time step approach, actually they often give you a choice of the type of length scale that you could be using. And you may see the options of conservative, aggressive, and user specified given to you as a user. And what they actually mean is that they're just different combinations of the two choices that we saw in the previous few slides. So if we thought about this case of the conservative case, then the CFD code will take whichever is smaller of the cube root of the cell volume and the maximum length of the domain. So what that means is that the length that it's taking is going to be smaller, and when you divide, when you use that length to calculate the propagation time will be smaller, and so a smaller pseudo time step will be used if you use the conservative approach. And that of course means that the calculation is likely to be more stable, because that diagonal term on the A matrix is going to be larger, but you're going to require more pseudo time steps to achieve your final converged steady state solution. And of course the opposite occurs if you click the aggressive approach. It's going to end up with a larger pseudo time step, which means you get to your steady state solution quicker, but you're more likely to get oscillations along the way. And there is a third option here, which is user specified, where if you have a complex CFD domain, or perhaps if you've had a look at your CFD domain yourself and you've got a better idea of actually what the characteristic length scale is that you're interested in, then you can often just specify this directly, which will be better than the automatic approaches where the CFD code just looks at your domain and just tries to guess what the length scale would be. And of course, if you really don't know, and in most cases, you can probably just start with the conservative approach, and then if your simulation appears to be stable but isn't really that converging that fast, you can then switch to an aggressive. And this is usually the default that's given for these CFD codes. Now we can move on to look at the second component of calculating that pseudo time step for our CFD domains, and that's looking at the velocity scale, or the characteristic velocity that boundary effect is going to propagate across the domain. And for this lecture, this is part 2, I'm going to focus on the velocity scale in solids. And then in part 3, which is the next talk, I'm going to look at the velocity scale in fluids because it's a bit more involved and there are more mechanisms to think about. And the reason I'm going to think about solids first is the only boundary effect that we need to think about is the propagation of heat from one end of the solid to another. And that's generally because the solid isn't moving, it's often a stationary wall, and the only thing we need to think about is the solid heating up and transporting heat across it. And so this will be a much simpler case for us and easier for us to derive a characteristic speed for how the effect of thermal boundaries propagates through a solid element. And the example I'm going to use is a popular example that I've used in quite a few of my previous talks, and that's just the case of 1D heat conduction in a bar. And at the left-hand end, the bar is hot, and the right-hand end, the bar is cold. And under steady-state conditions with no sources of heat in the bar, the steady-state temperature profile is linear, going from hot at one end to cold at the other end. And of course, under steady-state conditions, the temperature profile is linear, the temperature gradient, dt by dx, is constant and is the same along the bar. And that also means that the heat flux is constant along the bar as well. So if you think about between two solid elements in the bar, if you think, for example, of element 3 and element 4, the temperature gradient between these two centroids is a constant, and that gradient multiplied by the thermal conductivity of the bar and the cross-sectional area of the face gives the heat flux. And as we move from cell to cell, the temperature gradient is constant along the bar and the material properties are constant. So in this example, we've just got 100 watts of heat that are going across all of the cells of the bar, and the net effect will be 100 watts of heat transferred from this left end to this right end. And this is under steady state conditions. What we want to know about is under transient conditions or under pseudo-transient conditions, when we're building up to this steady state solution, how fast do the effect of these boundaries, the hot and the cold boundary, propagate along the bar? What speed do we need, that characteristic speed u0? And the way I'm going to demonstrate this is with the simple case where we start with steady state linear temperature profile along the bar. This could be your initial guess, this initial condition. And then at time 0, what's going to happen is, just for this example, the temperature at the left end of the bar is going to suddenly increase. And what we're going to do is use this example to look at how fast the effect of this boundary change propagates along the bar. And immediately you can see here that immediately after this heat source is increased at one end of the bar, the temperature of that wall is going to be suddenly a lot higher than it was before. And so what happens to the temperature and the heat flux in the bar, and how does it propagate along the bar? Well, if we look at this left wall here between the cell centroid and the wall, well, the temperature has suddenly increased, and so the temperature gradient between the wall and the centroid, dt dx, has suddenly increased. So now, for example, say we're getting 120 watts of heat coming into the left end of this cell in the bar. And of course, initially at the moment the temperature increases, we've still got the same temperature profile along the rest of the bar, and dt dx, or the rate of change of temperature with distance, is still the same as it was before. So we've got 100 watts of heat coming out the right end of the bar, and we would have 100 watts of heat going through all of the other cells in the bar as well. So if we think about this first cell, we've actually got a thermal energy imbalance between the left face of the cell and the right face of the cell there. So we've got, for this particular cell at the end of the bar, we've got 120 watts of heat coming into the bar, and then we've got 100 watts of heat going out. So there's a missing 20 watts of heat. Where does this 20 watts go? Well, of course, the answer is that in this transient case where the temperature is varying with time, the missing 20 watts increases the internal energy, or you can think of this as the thermal energy of the cell. And of course, watts, an easier way to interpret 1 watt is 1 joule per second. So what this actually means is that every second we've got 120 watts of 120 joules coming in, 100 joules going out, and then 20 joules are increasing the thermal energy of the cell, or 20 joules are accumulating in the cell. You can think of it that way. And so you can also think of this as a dq dt, or the rate of change of thermal energy of this particular cell is 20 watts, or 20 joules every second are accumulating in the cell. And we could also replace this Q, the internal energy, with MCPT, where M is the mass of the cell, Cp is its specific heat capacity, and T is its temperature. So what this really tells us is that because we're considering a solid element here, a solid element of bar, rather than a fluid or a gas element of a mesh, for example, that internal energy that's accumulating in that cell in the bar is going to manifest itself as an increase in temperature of that particular cell. So the way to think of this is that we've now suddenly increased the heat source in the left end of the bar. So there's 120 watts coming in, 100 watts going out, and the internal energy of this particular cell in the bar is increasing by 20 joules every second, and that's manifested in an increase in the temperature of this cell of the bar. So the temperature is going to start to increase. This temperature on the plot is going to start moving up. And of course, that temperature will increase, and as it does so, the temperature gradient between the centroid and the next cell is going to increase. So you can see here that this gradient has now gone up. And of course, as the gradient goes up, the heat flux, which is Ka dt dx, which we saw before, the heat flux out of the right end of this cell is also going to increase. And as the temperature of this cell moves up, the gradient increases until we reach a point where we have 120 watts coming in, 120 watts going out, and so there's no more accumulation of internal energy or thermal energy in this particular cell. This cell is now balanced in terms of its energy going in and energy going out. But what happens now? This first cell is balanced, its energy flux is balanced, but if we now think of the second cell in the mesh, this cell now has 120 watts coming in from the left end and only 100 watts going out at the right end. And so the same process is going to happen again. This cell is going to start accumulating internal energy, it's going to heat up, and that's going to increase its temperature. And so what you can start to see now is that the effect of this boundary here, this sudden increase in the thermal energy supplied to the bar, or a sudden increase in temperature, is propagating along the bar, where we're heating up the left end, then the second cell, then the third cell, then the fourth cell. And this process is going to continue until all of the cells have heated up and a new steady state solution has been reached. And you can see in this graph that the overall gradient, of course, is steeper because we've got a larger temperature difference between the left end and the right end, and we've now got 120 watts going between each of the cells in the mesh, and this results in a larger gradient between each of those cells. So that process of the temperature increasing and moving along the bar is repeated until a new steady state solution is reached. So this is the overall process for how thermal energy and heat is going to be transported in a transient manner along the bar. And what we've actually just seen there is we've seen the effect of a boundary propagating across the domain. This is the thing that we're interested in when we're specifying a pseudo time step. We want to know what is this speed that the effect of the boundary is propagating across the domain. And if we really think about it, the speed of the propagation in that example we just saw depends on how fast the temperature of that cell increases in response to the energy imbalance between the left and the right faces. That as this cell was accumulating internal energy at a rate of 20 joules every second, its temperature was increasing. And it's the rate that this temperature increases which is of course going to control how fast the effect of that boundary is going to propagate cell by cell across the bar. And it also depends on what is this temperature gradient and how much of a temperature gradient do we need to transport that extra 20 watts of heat to the next cell in the mesh. So we've got two processes here that are controlling the rate that the boundary effect propagates across the domain. We've got the speed that the element in the bar heats up, and then we've got the temperature gradient that's needed to transport that excess heat along to the next cell in the mesh. And of course, if these processes are faster, then that's going to result in a faster propagation speed U0. And in order to quantify these effects, we're actually going to end up introducing a quantity known as the thermal diffusivity. And don't worry if you don't know what that quantity is. I'm going to be deriving it using this example so you fully understand how we use it to calculate the pseudo time step. So if we think back to that first element in the bar we had at the left-hand end, where initially when we're at time equals 0, we have 120 watts coming in the left face of that element, and we have 100 watts coming out the right face of that element. We have a difference in thermal power of 20 watts between the left face and the right face. So you could describe this as a delta Q. A delta Q, and there's minus 20 watts, there's 20 watts less coming out of the cell than we've got going into the cell. And this difference in thermal power will be equal to the rate that the internal energy increases in the cell. And that makes sense. The difference between in and out will be equal to the rate of accumulation of thermal energy in the cell. And as we saw before, because this is a solid element, that's going to be equal to mCp(T), where m is the mass of this particular cell, Cp is its heat capacity, and T is its temperature. And even intuitively, just looking at this quantity, if this element of bar has a large specific heat capacity or a large mass, what that means is that for a particular difference in thermal power between the left and the right end, the temperature increase is going to be very small. So if we have a large specific heat capacity, the temperature difference or temperature gradient in time needed to balance the difference in thermal power between the left and the right ends is going to be very small. And the next thing we're going to do in this derivation is just replace the mass of the cell m by its density multiplied by its volume. And we're going to describe the volume of the cell as the delta x, its length in the x direction, and then A being the cross-sectional area of the bar element. So we're just going to write the mass of the cell as rho A delta x. And we're going to substitute that into our expression, equation 10, and we use that and get to equation 11, where all we've done is replace the mass by rho A delta x. The next stage in the derivation is just to divide both sides of the equation by A delta x, because of course these don't vary with time, so we can take them outside of the derivative and divide both sides by A delta x. And what we've done here is we've considered a cell in the bar that has a finite width delta x, and it also has a finite difference in thermal power between the left and the right faces. If we take the limit as the length of that bar cell tends to 0, then we can arrive at this form of the differential equation, equation 13. And the final stage in the derivation is to replace that thermal power, that Q, by Fourier's law, which of course we used before. Q is Ka dt dx, where K is the thermal conductivity, A is the cross-sectional area of that cell in the bar, and then dt dx is the temperature gradient along the bar. And we substitute that in for Q and then rearrange, the areas cancel, and we arrive at equation 16, which is the unsteady 1D heat conduction equation for solids. And you've probably seen this equation before. It comes up fairly often in engineering and heat transfer. But the important thing with going through the derivation, which we just did there, is you saw where these terms arose from and what they actually mean as they relate to our example. And it's really important that we understand it, because that's going to allow us to derive the thermal diffusivity and understand how that relates to the pseudo time step. But broadly, how you can think of this equation is, if you think of the right side, this is telling us that if there is a spatial difference in the temperature gradient, if there's a temperature difference suddenly caused by a change in the boundary, for example. If we suddenly take the left end of our bar and make it really, really hot, all of a sudden there's a change in the spatial temperature gradient at that end of the bar, and the left side of the equation is going to tell us the effect that that has in time and how that effect of that boundary propagates through the bar in time. And that's why you've got the time derivative here and its effect on the change in temperature with time. So hopefully from the preceding example that I went through, you can start to see what this half of the equation actually represents and what this half of the equation represents. And of course, if you look closely at it, what you'll notice is that because this left-hand side of the equation controls how fast places in the bar heat up in time, and then the right-hand side controls how temperature gradients propagate in space, we could, of course, for our real CFD domain, have differences in the density, the specific heat capacity, and the thermal conductivity of our solid. It may be a solid with properties that vary, and so, of course, that means that with this 1D heat conduction equation, that the speed that that boundary effect propagates can actually vary through our solid domain, depending on how we had it set up. And of course, areas with lower specific heat capacity would heat up really, really fast and have faster propagation speeds, whereas areas where the specific heat capacity were really low would take a lot longer for that boundary effect to propagate from the left end of the bar to the right end. But for our calculation, we only want a single pseudo time step, delta t. We don't want this to vary across the length of the solid bar. We want a single pseudo time step. And so what CFD codes do when they're calculating this pseudo time step is we just take an average of the material properties through that particular domain. So we take the volume average of the density, the specific heat capacity, and the thermal conductivity, and that's sort of going to tell us the average speed that the effect of that boundary is going to propagate through the domain. It may start fast and then slow down, but we only want a representative speed so that we can use that for the pseudo time step. So because rho, Cp, and K are now averages, they don't vary in space, we can just take those outside of the derivatives, which allows us to arrive at equation 18. And then if we divide both sides of the equation by rho Cp, we arrive at this form of the 1D unsteady heat conduction equation, equation 20. And you may have seen this before. This is exactly the same as the equation we introduced on the previous slides, but alpha has been introduced, which is the thermal diffusivity, or the average thermal diffusivity for the entire domain. And this equation is really, really simple. It encapsulates everything that we've looked at in the previous derivation and set of equations. And alpha physically represents that balance between the effect of the bar heating up with time as it accumulates internal energy and the temperature gradient that's needed to transport that heat away from that particular section in the bar. So you can even see from the quantities here, you've got K, the thermal conductivity on the top, which is governing that temperature gradient in space, and then you've got rho Cp, which is often called the thermal mass, which is controlling how that bar heats up in time. And this quantity captures the effect of that boundary propagating across the domain, and we can use it directly to calculate the representative speed that we need for the pseudo-transient calculation. And the easy way to do this is just to notice that alpha, the thermal diffusivity, has units of meters squared per second. So it's almost got the right units of meter per second, which is what we want. And all we need to do to get to our representative speed is to just divide alpha, the thermal diffusivity, by our representative length scale, which we looked at the start of the talk there. And I've just left up here on the slide the units on the right hand side of the equation so that you can check that the units do indeed check out and give you the right units that you want. And feel free to stop the talk and go through that for yourself if you want to convince yourself that the units are correct. But hopefully at this stage you can see that alpha, the thermal diffusivity, is capturing all of the physics that we're interested in. It's physically capturing the effect of that sudden change in the boundary condition propagating across the domain in time, and it gives us the right units as well. And so I just want to quickly wrap up with the overall process for how we specify that pseudo time step for solid domains in CFD. And the overall process is we start by taking that domain and ignoring the mesh, just looking at the entire domain as one continuous object. And then we start with calculating its representative length. And you could use the cube root of the volume or the maximum length of that domain, depending on what type of shape you've got. Once we've got the representative length for the domain, we then take the volume average of its material properties. If it's a solid domain, we calculate its average density, thermal conductivity, and specific heat capacity. Use that to calculate a thermal diffusivity for the domain. And then we just divide the thermal diffusivity by the representative length. And that gives us the representative speed for how a change in the boundary conditions, if it were to occur, would propagate through the domain. And the reason, of course, that's important is we do have a propagation of the effect of boundaries through the domain at the start of our calculation, because initially we start with an initial condition that isn't correct, and as soon as we click go, the effect of that boundary is going to propagate across the domain at this representative speed. And then, of course, we divide the representative length by the representative speed to get the representative time for the effect of that boundary to propagate across the domain. And then we take a fraction of that, which is the quantity f, and that gives us the pseudo time step size that we can then put into the matrix to stabilize the steady state calculation for the CFD code. And you'll notice that all of this can actually be done automatically. There's no need for user input. The user doesn't need to specify a value of, say, 0.3 or 0.7, which is what we did for relaxation. This process can all be done automatically by the CFD code, and as it captures the physical properties of the domain, it's more likely to give a balance between stability and speed that we need for getting a really efficient steady state calculation. Now, all of this was just done for solid domains. Much of it is similar for fluid domains, and I'm actually going to go through fluid domains in part 3 of this lecture series, which is the next talk. So if you're interested in how we do this, carry out this same process for fluid domains, stick around for the next part of this lecture series. So that brings me to the end of part 2 of my lecture series on pseudo-transients in CFD. I'm really hoping that by now you're starting to get a good understanding of what's actually going on behind the scenes in CFD codes when you select to use a pseudo-transient approach to solve your steady state calculation. Let me know in the comment section, did you find this talk useful? Did you learn anything or understand something that perhaps you hadn't quite got before? And are you looking forward to part 3, where I'm going to be going through the calculation of the characteristic speed in fluid domains, which are a bit more involved than solid domains, because we also have to think about convection and other effects that may be going on in the fluid domain. So I really look forward to hearing from you. Thank you very much for continuing to support the channel, and I'll see you in the next video.